sound, heat, light, they were all forms of energy. And now we get into another kind of energy, which is electromagnetic. Electric energy and magnetic energy. In this lecture, we are going to start off the whole topic of electromagnetism by talking of electric charge. What is electric charge? Well, it turns out to be a fundamental property of matter, just like mass is. But where does it sit? We can see a mass, we can see a particle. Can we see the charge? Where does it sit? We'll talk about that. And then, how can a body get charged? To start with, every body is neutral, no net charge. How can we impart charge to a body? So we'll talk of also the properties of charge and conductors and insulators. Conductors allow charges to move through them, insulators don't allow. And then we will start off the topic of imparting charge first to an insulator by the method of friction, and in the subsequent chapter we will talk about conductors and other methods of imparting charge. Welcome to the portals of real learning. Very exciting lecture. Obviously don't skip and listen carefully right till the end. So we come to the last chapter of the course, which is electricity and magnetism. As I said, this is also another form of energy. What we're going to talk about is static electricity, current electricity, and magnetism. Static is when we are talking of charges that are not moving. Current is when charges are moving. So what is charge? We need to understand that. And how do we make it move? Also, we need to understand that. And if we make it move, then what is the advantage? All that we need to understand. And the next is magnetism. Now you might wonder, how come we are talking about electricity and magnetism in the same chapter? Actually, electricity and magnetism are essentially two sides of the same coin called electromagnetism. And that's very, very interesting. So let's begin. We need to talk about charges, but first of all, in our day-to-day life, there are some manifestations of charge. One is lightning. During rains and thunderstorm, we have this lightning. What is lightning? It is a giant spark between, let us say, a cloud over here and the earth. During rains and thunder, the clouds come very close to the earth's surface. These clouds acquire what we call charge because they have come very close to the earth and they have a huge amount of charge. Then charge kind of leaks out and comes into the earth. That is lightning. And a lot of energy is released in the process. Something very simple that we keep seeing in our day-to-day life is if we comb our hair with a dry comb, we hear a crackling sound. If our hair is wet or the comb is wet, then we don't hear this crackling sound. If this truck was carrying, let us say, an inflammable liquid like petrol, it will be a big circular thing like this, cylindrical thing like this. You will find that these red things that I've drawn here are iron chains that are hanging from the body of the truck and touching the ground. And that is very essential for safety. Why? This petrol is highly inflammable. Some fumes may be coming out, and that is also very inflammable. And as the truck moves, the rubber tire is having some friction with the ground, because of which the whole truck gets charged up. And when it has got a charge, then a tiny spark may happen. Lightning is a huge spark, but even a tiny spark that can happen can ignite the petrol. And to make sure that such a spark doesn't happen, these iron chains, they take the charge safely out of the truck into the earth so that there's no chance of a spark. It is a safety device. Another experiment we can do is that if we have a glass rod and if we rub it with wool or silk, we find that it attracts pieces of paper. These are all manifestations of charge in our day-to-day life. So what is charge? Just like mass is a fundamental property of matter, charge is also a fundamental property. If you look at two masses, they exert a force on each other. We learned that in gravitation. If there are two masses at some distance, let us say r, and let us say one mass is m1, another mass is m2, they attract each other with a certain force F. And this force is given by Newton's law of gravitation, where capital G is a constant, then product of the masses divided by the square of the distance between them. And this is always an attractive force. Two masses attract. Mass is a fundamental property of matter. But if I have two electrons, and electrons are subatomic particles, we will learn about that. These electrons, they repel each other. So electron I'm going to show as a negative charge, and there's some distance between them. They repel each other. Let me call it the electric force of repulsion. But why don't they attract each other? They have got a mass, right? Newton's law of gravitation should apply. So yes, that gravitational attraction is there, no doubt about it. But the electric repulsion is stronger, therefore it repels. And this electric force of repulsion is having a very similar expression for this gravitational force. Some constant k is involved, and let me call this charge q1 and this charge q2. So it is product of the charges now instead of product of the masses divided by square of the separation between them. Two electrons repel despite the gravitational attraction between them. And there's another particle which is a positively charged particle. Electrons and protons attract each other. So if I have an electron which is a negatively charged particle and a proton that is a positively charged particle, apart from the gravitational attraction that is always there, they also have an electric attraction. So what we see here is that charge is also a fundamental property of matter, but unlike mass, there's only one type of mass. There is nothing like positive mass or negative mass. But in terms of charges, we have two types, negative and positive. Negative charge will repel each other. Negative positive charges will attract each other. And positive charges will also repel each other. We say that like charges repel and unlike charges attract. So charge is a fundamental property of matter by virtue of which two bodies may attract or repel each other. It's a fundamental property. But that charge needs to sit on a particle. It needs to sit on an electron, it needs to sit on a proton, it needs to sit on a metallic ball. It needs some body on which it can sit. It needs a particle. Now, the SI unit of charge is called Coulomb, named after the scientist Coulomb, and this SI unit is C. But when we talk of charge, we usually use the symbol small q or capital Q. The origin of charge is right at the atomic level. If you look at the atomic structure, a very approximate picture of the atomic structure is here, that we have a small part of the atom called the nucleus, which has got this red and blue balls. The red ball is a proton, which is a positively charged particle, and the blue one is another particle called neutron. Neutron has got no charge, therefore, very aptly it is called neutron. It is neutral. And around this nucleus, electrons are going around in some kind of a path. This is a very approximate model, of course. But it is useful to understand the atom to some level. Now, the electron is negatively charged and proton is positively charged. The amount of charge on an electron is negative minus 1.6 into 10 to the power minus 19 coulombs. And the charge on a proton is exactly the same magnitude but positive. And in any atom, the number of electrons, I'm going to write that as E, is equal to the number of protons in any atom. Therefore, since the amount of charge on each is the same, but one is positive, one is negative, and the number of them is the same, therefore, all atoms are electrically neutral to start with. Every single atom, copper, iron, any atom that you might think about, every atom is electrically neutral. So, how does it acquire a charge? Well, we can impart a charge to an atom by removing or adding electrons to it. If we remove, let us say, one electron from an atom, just one electron, then earlier the number of electrons was equal to the number of protons, but now it is one less, right? So the number of positive charges now exceeds the number of negative charges. Therefore, by removing, we make the atom a positive body and we call it ion. When an atom gets charged, we call it ion. If we remove an electron, we are reducing the amount of negative charge. Therefore, positive charges are in excess. So the atom becomes a positive ion. We can add electrons also. If we add one electron to an atom which originally was neutral, then the negative charges are in excess. In this case, the atom will become a negative ion. So we can add or remove electrons very easily. You might think, why are we not talking about adding or removing protons? Suppose we remove the proton from the nucleus, then one positive charge is less. That means it has got excess negative charge, then it becomes a negatively charged ion. If we remove a proton, it becomes a negative ion. If we add a proton, it will become a positive ion. So, yes, we could think about doing it, but it is extremely hard. Electrons can be added or removed very easily, and we're going to see some methods. But adding or removing protons is very hard because protons are held in a very small space called the nucleus. And apart from this electric repulsion, there is another force that is acting in the nucleus called the nuclear force, which is a very strong attractive force, which is what holds the protons together. If I have to remove a proton from the nucleus, I need to overcome that very strong attractive force that is there due to the nuclear force. Therefore, we don't really talk about adding or removing protons if we want to impart a charge to an atom. So let's only talk about adding or removing electron. So how much charge can I give to an atom which was electrically neutral? If one electron is removed, then it becomes a positive ion. Then the charge on the ion now is equal to the net charge, rather. The net charge is the positive charges are in excess is plus 1.6 into 10 to the power minus 19 coulombs if one electron is removed. If two electrons are removed, then the net charge on the ion will be 2 times 1.6 into 10 to the power minus 19. If 10 electrons are removed, then the net charge on the ion will be 10 times 1.6 into 10 to the power minus 19. It means that we can impart charge to an atom only in multiples of this number called 1.6 into 10 to the power minus 19. Only in multiples of that. I can't remove 1.5 electrons or 1.75 electrons or 2.8 electrons. I can add only full electrons or I can remove full electrons. So therefore, when we impart charge to an atom, either by removing or adding electrons, it is always in multiples of this number 1.6 into 10 to the power minus 19. Nothing in between. Nothing in between. And we say that this is actually a quantization of charge. Quantization of charge. I can give you charge only in terms of this thing. Let me call this number as E. Let me call this number as E. Then I can give a charge to an atom plus E or plus 2E or plus 3E or anything like plus NE where N is an integer. Or I can impart a charge by adding electrons minus E or minus 2E and so on minus NE, nothing in between. So this is called quantization. To give you an analogy of quantization, you have your fan regulator at home. So one type of regulator is like a big knob where one thing is marked as off. Normally the pointer is here, and then there are some markings here 1, 2, 3, 4, 5. So when the pointer is here, the fan is off. You hold the knob and turn it to 1, then the fan starts rotating at a small speed. You turn it to 2, higher speed. You turn it to 3, 4, 5, higher and higher speeds. 5 is the maximum speed. So what speeds can I give to the fan? Only 5 types of speed I can give. I can keep the knob either at 1 or 2 or 3 or 4 or 5, nothing in between. So we can give 5 different speeds to the fan with this kind of a regulator. But there's another kind of a regulator which is a tiny button like this, where an off part is there and an completely on part is there. Now, there are no other markings. So I can hold that knob and turn it from off, then fan starts rotating. I can put that position of that knob anywhere that I like. It is not 5 positions. I can put anywhere, slightly more, slightly more, slightly less. I can do all of that. So which means theoretically speaking, I can vary the speed in a continuous manner between 0 and a certain maximum. Maximum I'll get when it is in the on position. Between 0 and a certain maximum, I can impart any speed to it. So then that is not quantized, whereas this is quantized. Clear? So let us do two small sums. What is the amount of positive charge, negative charge, and total charge in one atom of oxygen? One atom of oxygen has 8 protons and 8 electrons. Okay. So the first part is the amount of positive charge is equal to the protons, that is equal to 8, and each proton has got 1.6 into 10 to the power minus 19 coulombs positive. That is the total positive charge on the oxygen atom. What is the total negative charge? The number of electrons are the same as the number of protons. So it will be the same number, 8 electrons are there, same amount of charge but negative. That is the total negative charge. And what is the total charge? When you add up, that is 0. That is what we mean all atoms are electrically neutral. Another sum. How many electrons do we need to make up minus 1 coulomb of charge? So one electron has got a charge of minus 1.6 into 10 to the power minus 19 coulombs. If I want 1 coulomb of charge negative, how many electrons do I need? So it will be 1 into minus 1 divided by minus 1.6 into 10 to the power minus 19 This goes off. 10 to the power minus 19 goes up as 10 to the power plus 19 divided by 1.6. So it is 1 by 1.6 into 10 to the power 19. This will turn out to be 6.25 into 10 to the power 18. Just look at this number. 10 to the power 9 is billion. This is billion, billion, or much more than that. Huge number of electrons are required. So electron has got a very tiny charge. Okay. What are the properties of charge? It is a scalar quantity. It's not a vector. It can be added because we are giving it a number as well as we are giving it a sign plus or minus. We can add them algebraically. Net charge is always conserved. Charge can never be created or destroyed. We can remove an electron from one body and put it on the other, but the net charge is not going to be altered. Charge on one body will get altered if we add or remove charges to it, but the net charge in the whole universe will stay constant. Charge cannot be created or destroyed. So there's a law of conservation of charge which is extremely important. Third, it is quantized, but mass is not quantized. I can give you any amount of mass that you want. Very tiny, tiny masses I can give you. Charge is invariant. Some body has got some charge on it. If you apply some pressure on it, if you heat it up, or you do any kind of a process on it, the charge on it doesn't vary. Also, if the body is moving or not moving, accelerating or not accelerating, all that doesn't alter the charge on the body. It is invariant to those physical processes. And very interestingly, charge produces electric and magnetic effects. Electric effect we have just talked about, that is, one charge exerts a force on the other. Actually, more accurately, one charge sets up something called a field, which then exerts a force on the other. We'll talk about it. But yes, charges have electric effects. But how do charges have magnetic effect? That's a very, very interesting part of this chapter. There are some bodies which allow charges to move through them. First of all, let's just go back. We said that every atom has got electrons and protons. Every single atom. Whether you talk of wood, for example, which is not an element, it is a compound, primarily carbon and hydrogen and some other things. If you talk of anything, it has got atoms in it. Every atom has got charge in it. Every atom is electrically neutral, but you can't say there is no charge within the body. There's a lot of charge. There are billions and billions of electrons and protons in that body. Every single body has got a lot of charge, but no net charge to start with. And we find that charges can move around. Suppose there's a free charge, it can move around from one place to the other in some bodies, but cannot move in some other bodies. So those bodies that allow charges to move through them are called good conductors or simply conductors of electricity, and those that don't allow are called insulators. Why are conductors conductors? What makes them a conductor? Well, it so happens that they have mobile charges. If you look at an atom, the protons, the neutrons, and the electrons are all bounded within that atom. Nothing is free to move around within the body. Mobile charges means it could be an electron or it could be an ion, positive or negative ion that can move around. So if they can move around within the body, then they are good conductors. Otherwise, they are bad conductors or insulators. Examples: all metals are good conductors. You can see this metal. Acids are good conductors. Impure water is a good conductor. Impure water, which contains some salts and minerals, etc. Insulators, they don't have such mobile charges, that is, charges that are free to move around. Examples are wood, glass, plastic, rubber, etc. So, one example I can give you is that you have this plug in your house. There's a one big plug and there are two small. There's a plug in which you plug on some appliance and use it, right? Now, don't try this at all. I'm just saying if accidentally somebody put an iron wire inside this hole, he might get an electric shock. That can be very dangerous. Don't try that. But if somebody inserted a wooden pencil inside that hole, he won't get a shock because wood doesn't allow the charge to flow through the wood. And our bodies are good conductors. If I poke an iron wire in that hole, then charges flow through that iron hole through my body into the earth. And the very process of that charge flowing through my body can be fatal, can be fatal. But wood doesn't allow, rubber doesn't allow, plastic doesn't allow. So you'll see electricians who are working with devices, they will always wear rubber gloves before operating something. Or they will wear rubber boots. Basically, charge should not flow through the body. So even if the boots are worn, charge comes, let us say, from your hand up to the leg, but then it gets stopped because it can't flow. So let's talk about imparting charge to a whole body. There are three methods: friction, conduction, and induction. Let's talk about friction. If you take a glass rod and rub it with silk, then glass becomes positively charged. If you take ebonite, which is rubber, rub it with wool or fur, then the ebonite becomes negatively charged. You'll see these experiments also. If you take a balloon, simple balloon, and rub it against your t-shirt, then it will stick to your t-shirt. Similarly, a glass rod rubbed like this will later on attract small pieces of paper. This boy's hair is standing up because he just combed his hair with a dry comb, and some charges have come on to his hair, and those charges are all of the same type. Therefore, they are repelling each other, and hence the hair stands up. Now, this is charging by friction. Glass and rubber are insulators. We can charge it simply by holding the glass rod in one hand and rubbing one end with silk. Then that end that we rub becomes positively charged. What happens is that when we do this rubbing, friction is happening and we are knocking out electrons from the glass onto the silk. So if somebody loses electrons, he becomes positively charged. So therefore you have a net positive charge. And by the way, the silk will become negatively charged because it has gained electrons. In the case of ebonite, when you rub, then electrons are knocked out of the wool and then they sit on the ebonite. So ebonite becomes negatively charged and the wool will become positively charged. So such a simple way we are able to knock out electrons. And we are creating charged bodies. The glass is positively charged, the silk is negatively charged. Similarly, the ebonite is negatively charged, the wool is positively charged simply by friction. And the electrons that got knocked out from this region, they are leaving behind positive ions. They cannot move around. So they just stay there only because insulator will not allow charges to move around. Similarly, here, negative charges are created, negative ions are created, they are not allowed to move around. Simple charging an insulator by friction. Now, these glass rod or rubber rod can attract pieces of paper. Paper is neutral to start with. Why does this glass rod attract paper? Now, suppose I bring a piece of paper over here. I bring a piece of paper over here. Paper is neutral, like every other element, every other material, rather, not element, is neutral. But the existence of this positive charge over here exerts forces on the atoms of the paper. Electrons are attracted because unlike charges attract. While the atom inside the paper is stuck, paper is a solid. In a solid, atoms cannot move around. In a liquid, they can move around. In a gas, they can move around. This is a solid, so it is not that one atom will go from one place to the other. But within an atom that is closest to the glass rod, the electrons are getting attracted and the shape of the whole thing changes within the atom. And hence, while the nucleus of the atom is getting repelled, so let me show a simple picture. Electron comes closer, the shape of the atom changes, whereas the positively charged nucleus is away. So now this guy will get attracted, this guy will get repelled, but the electron is closer. Therefore, since the force is inversely proportional to the square of the separation, the attraction of the electron is stronger than the repulsion of the positive part of the atom, therefore, net attraction. So the paper sticks. And wonderfully, another piece of paper can be made to stick, and we can make a chain of paper like this. Same thing happens. This positive has come here, inducing some electrons to bend towards this side, and positive here, positive here, negative here, like that. So we can kind of make a chain, but not a very big chain. And not, let's say, pieces of iron. It is only paper that can be attracted because the amount of charge is small and the force also is small. The weight of the entire chain has to be supported, right? So the force is not that strong to support, let us say, a chain of iron nails, but paper, yes. All right. That is why you see this experiment. And same thing happens if you comb your hair, then electrons are moving from one body to the other. And if you bring after that the comb close to your hair, the hair will stand up, getting attracted towards that. Let us say the comb lost electrons. Suppose while combing, the comb lost electrons. So comb became positive and your hair became negative. Now, if you bring the comb close to your hair, positive and negative will attract each other. That is why the hair will stand up. So that's one method of charging an insulator by friction.